To see application of residues to evaluate real integral. Here we are having two types. First, let us see type 1, that is integral 0 to 2 pi f of cos theta comma sin theta d theta, which means that here the integration will be in terms of, that is, a function will be in terms of cos theta and sin theta, where f is the rational function. Okay, and here the integration is taken around the unit circle. Actually, from 0 to 2 pi itself it is a circle, but here we are considering the unit circle. Unit circle means we are considering the circle to be of radius 1. So while evaluating this integral, we have to consider only the unit circle. So before moving to the problem, we have to know few notations. So here we can represent a complex variable z in terms of r into e power I theta. Generally we know that z is equal to x plus iy, which is in Cartesian form. In polar form, if we want to represent a complex number, we can write it as z equal to r into e power I theta. So here r is the radial length, and here since we are considering the unit circle, the radial length is 1 here. So we are taking r is equal to 1 because of unit circle. So we can write z is equal to simply e power I theta. And then here we are differentiating at both the sides. So dz becomes I into e power I theta d theta. And then here again this e power I theta can be replaced as z. So finally we can write d theta is equal to dz by iz. Why we are doing these things is, here the question is in terms of theta, that we have to convert it in terms of z. Okay, and then we have to do the integration. So because of that we are converting everything in terms of z. So that here we are taking z is equal to e power I theta, so that d theta can be written as dz by iz. Again, what about here cos theta and sin theta? This cos theta and sin theta should also be replaced in terms of z. So already we know that by Euler theorem, e power I theta can be written as cos theta plus I sin theta. Similarly, e power minus I theta can be written as cos theta minus I sin theta. So from this, or adding these two, we can get cos theta is equal to e power I theta plus e power minus I theta by 2. Similarly, sin theta can be written as e power I theta minus e power minus I theta by 2i. Now this e power I theta, we know that already we can replace it as z. So we are replacing in terms of z. Again, because of this minus I theta, we can write it as z power minus 1. Simplify this. We will get finally cos theta as z square plus 1 by 2z. Similarly, here if we simplify for sin theta, we will get sin theta z square by, z square minus 1 by 2zi. Now let us see the question. Here we have to evaluate integral 0 to 2 pi d theta by 13 plus 5 into sin theta using contour integration. Contour integration is nothing but we are considering the circle, unit circle, that is we are doing the integration around the unit circle. So that is called as contour integration, that is closed circle. And then here, as I told you, this integration is in terms of theta, right? These theta terms should be replaced in terms of z. So that here we have to remember first z is equal to e power I theta. So that d theta can be replaced as dz by iz. And similarly, whether if the function is in terms of cos or sin, we can replace like this. Here in this question, we are having only sin theta, so that we can take sin theta as z square minus 1 by 2zi. So that here this question, that is integral 0 to 2 pi d theta by 13 plus 5 into sin theta is the given question. This we can return in terms of the unit circle C. For this we can mention like this. Because of circle or closed curve, we are representing the integral symbol like this over the circle C. Okay. Now d theta. What to replace as d theta? D theta can be replaced as dz by iz divided by 13 plus 5 into sin theta can be replaced as z square minus 1 by 2zi. Clear? Now we have to simplify this. While simplifying this, we will get dz by iz divided by, if you simplify, take LCM, it becomes 13 into 2zi becomes 26zi zi plus 5z square minus 5 divided by 2zi. Divided by 2zi can be taken to the numerator as 2zi as product in the numerator. So this zi and this zi get cancelled. So numerator will be 2z divided by this term. Now we can have the integration like this. Now we have to factorize the denominator. Denominator is a quadratic in terms of z. So as usual, by using the formula minus b plus or minus root of b square minus 4ac by 2a, using that if we find the roots, we will obtain the roots as z is equal to minus I, that is complex roots we will get minus 5i and I by 5. So out of these two, we are considering the circle to be the unit circle. If you consider these 2 points, in these 2 points, this minus 5i alone, that is I by 5 alone, lies inside the unit circle C. Clear? 5i will be outside the circle. So we have to consider the points, and moreover if we find the roots, why we are finding the roots is here these two roots are called as poles. Okay, so out of these singular points, we have to identify which singular point lies inside the given closed curve C. So here minus I by 5 alone lies inside the curve C. So we have to find out the residue for this point. Let us factorize the denominator. So this can be written as 2 dz by, since coefficient of z square is 5, we have to take 5 outside, and then already the roots are minus 5i and minus I by 5. We can write the factors as z plus I, 5i, z plus I by 5. So if you multiply this term, we will get the quadratic equation. Okay, so please don't miss this 5 because the coefficient of z square is 5 here. So now we have to consider the poles which lies inside the circle. Already we have identified that z is equal to minus I by 5 lies inside the curve C, whereas minus 5i doesn't lie. So that here we have to find out the residue of the function f of z. F of z is nothing but the whole term at z is equal to minus I by 5. So the formula is, since z plus I by 5 is a simple pole, that is minus I by 5 is the simple pole because z plus I by 5 whole power 1 is given. So using simple pole, how to find out the residue? So z tends to minus I by 5 into, we have to write the function f of z. Before that here z minus a. Z minus a is nothing but z plus I by 5 into the function f of z. F of z is 2 divided by 5 into z plus 5i into z plus I by 5. Right? So now this and this get cancelled. For the remaining term, we have to substitute z is equal to minus I by 5. So minus I by 5 plus 5i is simplified as 25i minus I is 24i by 5 is the simplified term. So this is equal to 2 by 5 is already here, and 1 divided by 24i by 5 can be written as 5 by 24i. Clear? So this is equal to, we can simplify this and we will get it as 1 by 12i. Now what happened here is, this is the residue, right? Now by Cauchy residue theorem, integral over C f of z dz is the given question. This is equal to, the Cauchy residue theorem states that 2 pi I into sum of all residue. Sum of all residue means here we are having only one residue. So that we have to write it here. So the residue is 1 by 12i. So we can simplify this, cancel I and cancel this. So the final answer will be pi by 6. So the value of the integration is pi by 6.